blank. So in that blank, we'll put circle. Is the set of all points in a plane that are equidistant from a given point that we call the center of the circle. A circle with center P is going to be called circle P, so you name it based on whatever the name of the point in the center is, and can be written as circle P, so this is the notation for a circle. A segment whose endpoints are the center and any point on the circle is a radius. So you guys already knew that. If it goes from the center, so from here to the edge, like this line here, we call that a radius, right? A chord, which is going to be the next one we define. This one may or may not be something you've heard of before. A chord is a segment whose endpoints are on a circle. So this chord right here has an endpoint on the circle here and an endpoint on the circle here. So a chord is any segment whose both endpoints are on the circle, which would also be a diameter, right? A diameter has both endpoints on the circle, so it is a chord, but a diameter specifically has to go through the center as well, right? So that's this last one here. A diameter is a chord that contains the center of the circle. So you guys already knew what a radius and diameter were. Chord might be a new idea. It's just a segment who has both endpoints on the circle. It doesn't necessarily have to go through the center. All right? Okay, so then some new vocabulary. First, we're going to talk about a tangent. So a tangent, we've talked about tangents in our trig ratios, right? Now we're going to define what a tangent line is inside of a circle. So this is a line that intersects a circle at exactly one point. So it's only going to touch your circle at one point. For example, in this drawing over here, this line, RU, would be a tangent line because it only touches the circle once at point C. So we could say like RU, and remember for our notation to show that it's a line, we put arrows on both ends in the picture. So this line segment RU is a tangent line because it only touches the circle at one spot. Okay. Specifically, the point where it touches is called the point of tangency. So it's just that point where it's touching the circle. So this is the point on the circle where a tangent line intersects the circle. So in the picture here, what is our point of tangency? Point T. Good. Like point T in the picture. Good. Okay. Then we have what we call common tangents. A common tangent is a line that is tangent to two or more circles. So the same line is going to touch more than one circle at one specific place. So a line that is tangent to 2 or more circles. So an example of what that would look like would be either of these two drawings below, right? This line right here is tangent to circle S and to circle C, right? It touches each one of those circles one spot, so it's called a common tangent. Same thing here. This line right here goes in between circle S and C and is tangent to both of those circles. Okay, the difference between where these tangent lines are touching the circle is where they get these names internal and external tangents. Okay? So an internal tangent is going to touch your circles in between or on the inside. So this goes between the two circles. While your external is not going to go in between, it's going to be on the outside. So external tangent does not go between the two circles. Okay, so in this unit, we're going to have a lot of theorems. Remember, a theorem is basically just a rule that once we know what it is, we can use it to solve for missing pieces, right? So the first theorem has to do with our tangent lines. It says that if a line is tangent to a circle, so if a line touches a circle at one spot, then it is perpendicular to the radius drawn to the point of tangency. What does perpendicular mean? 90 degrees. Right, it's going to form a 90-degree angle at the intersection. So that's what's going to be important here, is that we know that it forms a 90-degree angle where some radius, which would be this segment here, intersects a tangent line, which is what this line is here because it intersects the circle once. Right? So where those two lines intersect, we know it's going to be perpendicular. Therefore, ST, the radius here, is perpendicular to the tangent line RT at point T. Okay? All right. The second theorem that we need to know that's going to help us find some missing pieces says that if two segments from the same exterior point so exterior means on the outside, right? So exterior point would be like point V here. If you have two segments that come from the same exterior point, like this one and this one, that are tangent to a circle, exactly like these two are here, then you're going to know that those two segments are congruent. So this piece and this piece are going to be congruent. Okay. The converse is also true. If they told you these two pieces are congruent, then you must know they're coming from the same external point and are tangent to the circle. Okay? So therefore, in this drawing, the segment TV is congruent to the segment RV. Okay? And that is only the segment between those points. So from R to V and from T to V. We don't care about the part that's after those points. Okay? We're just saying that these two segments are congruent. All right. So now that we know these two properties, we know where a radius intersects a tangent, we have a 90-degree angle, and we know if they come from the same external point, then two tangent segments are congruent. If you'll flip it over onto the back, we're going to look at some examples of how we can use this to find missing pieces. Okay, so in the first one here, we're just identifying things. So it says, use this picture to answer the following questions. I don't know really what happened, but it cut out some of my letters here, so we'll read it off of our paper. It says tangent to circle C, but not to circle S. So which one of these segments is a tangent for circle C, this one here, but not a tangent for the other circle? We're looking for the segment that's a tangent for circle C, but not circle S. SR, yes, very good. Right, this SR touches circle C on the outside edge once, but it doesn't do that for S. So SR would be the segment that's tangent to C, but not S. All right, B says we're looking for a tangent to neither circle. So which one of these lines is not a tangent for either circle? SC, right? SC does not just touch the outside edge of either one of these circles. So SC is not a tangent for either. Good. Okay. Now we're looking for a common external tangent. Remember, an external tangent means it has to touch on the outside of the circle. And which one would that be? PQ, very good. And then we're also looking for a common internal tangent. Which one is it? I think TA. I think Q is part of this one. Yeah. So TA. Yeah. Okay. So now that we can identify tangents, internal, external, all the things, let's actually solve for some missing pieces. So on number 2, it says circles T and R are tangent at point Q. So this circle right here with point R in the middle and the circle with T in the middle are tangent at point Q, it says. QW and SW. So from Q to W and from S to W. These are both tangents to circle T. They're really big circles. It says circle T has a radius of 24, QX is 5, and XW is 11. So we're going to first just go in and label all those pieces they just gave us. So they said the radius for T was 24. What's a radius again? Right. So I could go from point T to any edge, and it's going to have a length of 24, right? So I'm going to go from here to the edge and label that it has a length of 24, okay? They also said QX, which would be this portion here, has a length of 5, and XW, so from here to here, has a length of 11. And we're going to find all of these segments listed over here. Okay, so let's start with QR. So QR goes from the center of this circle to the edge. So any idea on how we could find the radius for circle R? Exactly, right. We know that from the center to any edge has a length of 24, and this is from the center to the edge again, so it should be half, right? So these would each be 12 and 12. So QR is 12, very good. Okay, they asked for QW, so QW goes from here to here, so all we would need to do is what? Add, okay, so we have our 5 plus 11, so QW must be good. All right, then they asked for TS. Well, TS goes from the center of circle T to the edge, so it must be a length of, good. Okay. All right, then they want RX. So RX goes from the center of circle R to this line here. Okay, so what we do know right now is that from Q to R is 12, from Q to X is 5, I'm looking for R to X. Well, what is that we just drew right here? A triangle. What kind of a triangle? A right triangle, because a radius and a tangent form a 90-degree angle. right? So what could we do to find the missing side in the right triangle? Right. So my A and B are the 5 and 12, right? So 5 squared plus 12 squared is equal to the missing side. The one we're looking for is our hypotenuse, our x squared. This is also one of our triples, right? So what is our missing side here? 13. Good. Okay. All right, the next thing they ask us for is SW. So SW goes from here to here. It should also be 16 because from Q to W was 16, then S to W is supposed to be congruent. So, right, this is congruent to QW, so also 16. All right, and the last one that they ask us for is RW. So R is here, W is here. Well, that still is a right triangle, right? Okay, so I know that one side of it is 12, plus this side up here, you guys said had a length of, right, equals that RW squared. So we actually could simplify these, and this is still one of our triples, or you can go ahead and solve it. So 12 squared plus 16 squared is going to give us, right? So 400 equals RW squared. We take the square root, so RW must have a length of, right. So with the theorems we know about what's supposed to be congruent or what forms a right angle, plus your prior knowledge of how to find missing pieces in right triangles, you're able to find a lot of missing segments with tangent lines. All right, number 3 says triangle TRW is circumscribed about circle A. If the perimeter of triangle TRW is 50, TK is 3, and WM is 9.5, find TR. So this might be a new term for us. Cut out a lot of my stuff here, didn't it? 50, TK equals 3, and WM equals 9.5, and find TR. Okay. All right, so circumscribed. This means that all of the sides that are outside of your shape are tangent to your circle, okay? So we might define that here so we don't forget that that's what it means. So this triangle circumscribes this circle because every single side of the triangle is tangent to the circle. All right. So because of what we know from the front page about if they come from the same external point, then the two tangent segments are congruent, I should know certain things. Like, for example, T is an external point, right? So from T to K is 3, then what should it be from T to L? Also 3. Okay? Right here, I know that from W to M is 9.5, so what else is going to be 9.5? Right. Okay? All right, so we already know a few of our pieces here. So we know that TR was congruent, or sorry, not TR, TK was congruent to TL because they both equal 3. And we know that KW and MW are congruent. So that means they both have to be 9.5. And if I'm finding the perimeter of this triangle, that means the only pieces I don't know are these two pieces here, right? Okay, so they told us the perimeter of this thing was what? 50, okay? If I know everything but these two pieces, what could we do to solve for those missing pieces? Right. Exactly, right, because he said we should divide by 2 because we know that these two pieces are going to be congruent, whatever they are. It'll be what's left over. Good. Okay, so we'll have 3 plus 3 plus 9.5 plus 9.5 plus these two pieces here. We'll call them x and x, which if I add those together is just 2x, right? Is going to equal that perimeter 50. All right, so I add all of my numbers here. We got 3 plus 9.5 plus 9.5. What does that give us? 25. Okay, so we have 25 plus 2x equals 50. Then what do? Right, and 50 minus 25 is just, right, and then what do? Divide by 2. What is 25 divided by 2? Very good. So x must be 12.5. So both of these segments are 12.5 because they had to be congruent since they came from that common external point. All right. Okay, we got one more here. It says that line M, so this is line M, they labeled it with that lowercase letter, is tangent to your circle A at the point B. So this is the tangent point, or the point of tangency. It says to find the radius of circle A and to find the slope of line M. Okay, well the radius of a circle goes from where to where? Center to the edge. So here's the point at the center, here's a point at the edge. How do you find the distance between 2 points? Distance formula, right. So just remember our distance formula is the square root of x2 minus x1 squared plus y2 minus y1 squared. Right, where these points over here are x1, y1, and x2, y2. All right, so we'll make A our x1, y1, and we'll make B our x2, y2. All right, so for finding the distance, I'll have the square root of x2 minus x1 is going to be what? Good. Squared plus y2 minus y1 will be good. Squared. Okay, so 1 minus 3 is -2, and -2 squared is 4. Okay, and -1 minus 2 is, and -3 squared is 9. And what is 4 plus 9? 13. Still under that radical. There is no perfect square root of 13, so we would just say the length of the radius is square root of 13. All right. Okay, the last thing they asked us to do is to find the slope of the line segment here. Well, we could find 2 points that we know for sure, but if your drawing isn't super clear, you may not be exactly sure where the next exact point is. However, I do know exactly where these 2 points are, right? So I can count my slope from one point to the next, right? My slope would be rise over run. To get from B to A, we rise how many? 3, and we run 2, okay? So we know that the slope of the radius is 3 over 2 because of the rise over run. And what do I know about the radius and the tangent line? They're perpendicular. So if this is the slope of the radius, what does the slope of line M have to be? Very good. Okay, so since M is perpendicular to